Only 11 more weeks. You guys are almost there. So the first reaction we're going to do this term is similar to last term. So last term we finished up talking about aromaticity. However, the only reaction we really covered was reaction at the benzylic position, right? Oftentimes chemists want to react on the aromatic ring itself. So let's say we've got benzene. A lot of beginning chemists will say, well, what if we treat this with Br2? Is it possible to get an addition reaction where you get bromine to add across one of those pi bonds?
Maybe.
Why not?
Isn't it too stable as a benzene ring?
Yeah, exactly. If we look at the starting material, right, this is aromatic. This is not aromatic. That means that this reaction is just not likely to occur, simply because that aromatic stabilization energy is huge, right? On the left-hand side, we're following Huckel's rule. So we've got 4n plus 2 pi electrons. On the right-hand side, we have sp3 carbons, right? So this reaction will not occur. You're kind of stuck at this point. However, there's this weird thing that happens when you throw in iron. So let's do the same reaction, but we're going to throw in iron. If you add iron to this reaction mixture, you can actually get bromine to add across, right? And if we look at this, this is okay because we went from aromatic to aromatic. This is referred to as electrophilic aromatic substitution. And why do you think it's referred to as a substitution reaction?
Because you're substituting hydrogen.
Yeah, exactly. You had a hydrogen off this position, but now it's been replaced with a bromine. It's not addition, it's a true substitution reaction. So let's go over the mechanism for this. And there's a wide variety of functional groups we can install onto aromatic rings using this electrophilic aromatic substitution chemistry. So the overall mechanism's a little bit tricky, but it always involves a really, really strong electrophile. Let me clean this up. And why do you think we have to use a crazy strong electrophile? It's a crazy strong aromatic ring. That's one way of thinking about it. So this must be super strong. And the reason for this is super weak. So if you have a weak nucleophile, a good workaround is to deal with a really, really strong electrophile and overcome that weak nucleophile. So in this case, we've got pi bonds that can act as nucleophiles. And it's pretty intuitive that one of them is going to reach out and attack our electrophile, right? Make sure that you have your arrows going in the right direction. Okay? And this always looks funny, but your product at this point, or your intermediate, I should say, has an electrophile, a hydrogen, and then a positive charge right there. Do you think this is very happy? No, absolutely not. This has broken aromaticity. We're going through a very, very high energy intermediate. This wants to quickly re-aromatize itself. So at this point, what we need to do is we need to clamp down using a base and restore aromaticity to the system. So at this point, we're doing pseudo-elimination chemistry in order to regenerate our aromatic ring system. This intermediate with that positive charge has a special name. Depending on what textbook you refer to, they call it different names. Some textbooks refer to it as a sigma complex. And other textbooks refer to it as an arenium ion. It doesn't really matter which term you use. It's tomato or tomato in my book. Does that make sense? This overall reaction scheme shows up again and again and again and again. The number one mistake I see people make is they put the positive charge on the wrong carbon atom. Make sure that positive charge is adjacent to where your electrophile was added on. It needs to be the carbon next door. So let's take a look at that halogenation reaction, and we'll go through and explain why iron helps that reaction occur. So we'll start out with that bromination one. And then we'll do chlorination too. So let's write out our overall reaction mechanism, or our overall reaction, and then we'll do the mechanism. I will say the chlorination reaction isn't really as common. Does anybody know why? It's a gas. It's hard to handle. Bromine's a liquid. It's a lot easier to work with. Okay, so I said with the bromination mechanism, it won't work with just Br2 itself. You have to add in iron. And the interesting thing is that if you have two equivalents of iron and you react this with bromine, you end up forming two equivalents of iron tribromide. So really, when you're tossing in iron, it's not the iron doing the chemistry here. It's that iron tribromide that's formed when the iron mixes with the bromine itself. So really, the active reagent here is this FeBr3, that iron 3 tribromide. With chlorine, same thing. You can't just have this react with chlorine gas itself. You have to add in a metal. And in this case, we don't use iron. Does anybody know another metal that might work?
Aluminum trichloride.
Yeah, aluminum. So in this case, you oftentimes use aluminum trichloride, and we'll show why these are so important. What are the geometries for iron tribromide and aluminum trichloride? I don't know. Are they tetrahedral, trigonal planar, trigonal pyramidal, bent, seesaw, octahedral?
Pure. No. What does that mean again?
All right, so let's go ahead and draw this out.
Tetrahedral.
So let's do the bromination mechanism. And let's do some review. So we've got iron. We've got one bromine here. Another bromine back here. Another bromine back here. What's the shape? No lone pairs? Trigonal planar, right? If it's trigonal planar, what hybridization is it? sp2. That means that this iron has this big old p orbital that is unoccupied. Does this make it a good Lewis acid or a good Lewis base? Oh man.
Makes it an acid. Acceptable.
It's like term 2 went in and term 1 fell out. All right, if it accepts electrons, that means it's a good Lewis acid, right? So in this case, empty orbitals mean that it's going to be a good Lewis acid. Okay, so let's make a note of that. So it's a good Lewis acid, meaning it'll accept electrons into that empty p orbital, which is good because we've got bromine hanging out over here. And bromine's got a large amount of electron density. And so one of these lone pairs can get donated to that empty p orbital. And when you do this, you do change the geometry of your iron complex. Your iron now has a formal negative charge. This the internal bromine has a positive charge. What's the geometry of your iron now?
No?
Tetrahedral, right? We look at our central atom, iron. It's got 4 electronic groups around it. It's tetrahedral. So in this case, we formed a Lewis acid-base adduct, right? Do you guys remember talking about that in first term? Lewis acid-base adducts are really common with these metal centers. And when we look at this, we've got to be able to identify where the dipole is in our molecule. So if we look at our dipole here, this bromine is super duper unhappy, right? It's got a positive charge. It's going to pull electron density away from the bromine next to it and away from that iron center. So in this case, there's a really, really strong net dipole here, which is good because that makes this a very good electrophile. Okay, so now that we've formed our super strong electrophile, we can treat it with our weak nucleophile, which we know is going to be that aromatic ring. And for most of our chemistry that we're covering this term, we're going to use benzene as our aromatic nucleophile. However, this does work with other aromatic ring systems like pyridine or furan or thiophenes and things like that. So you're not limited to just benzene. It will work with just about any aromatic system, and I'll make some challenge problems for you guys to work on those. All right, so now that we've got this, our nucleophile is going to attack our electrophile, kick off our leaving group. And our leaving group, I'm just going to call this FeBr4. And in this case, our iron still has that negative charge on it, right? Okay. So now that we've done this, actually, I apologize. I'm going to mess up your notes. I'm going to draw this out.
Can you go up a little bit?
Oh, yeah. So let me draw out our leaving group, because the leaving group is involved in the next step. This leaving group can actually act as a base, and it's going to do that E1 elimination type chemistry. So in this case, it's going to attack, deprotonate, clamp down, and our rhenium ion will now form our brominated product. And the nice thing with this is we regenerate our iron tribromide. So in essence, that iron tribromide is catalytic in this reaction. You don't need very much of the iron in order to help get this going along. Yep?
When we're doing this, how are we going to know? Are we just going to assume it's just one equivalent? Because what's to stop it from happening if you have the pair position or some other position?
We'll talk about that. As far as I'm concerned right now, if I don't specify more than one equivalent, you should assume only one equivalent. There are some reactions where you do run into that problem, where you have it react more than once, and oftentimes uncontrollably, and we'll talk about that. Bromination is actually a lot easier to control than some of the other reactions. The other side product that you get out of this reaction is HBr. So oftentimes you do have to be careful about your other functional groups present. So for example, if you've got an acid-sensitive functional group, that HBr that's your byproduct might do chemistry with your acid-sensitive functional group. So this does work well under some situations. Under other situations, you have to protect any acid labile functional groups. Does that make sense? Yep.
Well, do you kick off a bromine when the iron complex attacks?
Yeah, let me actually zoom in on this. I should clarify this arrow a bit more. So at this step, it is this bond right here that is actually doing that deprotonation. So that bromine is acting as the base. Yeah, it's a little weird to think about it, right? A Lewis acid-base adduct is in equilibrium. So if you really have a little bit of Br minus around, that's a really weak and reversible bond. All right, let's do the same thing with chlorination. And at this point, you guys should be capable of figuring out this one on your own. Here, let me... All right, so with the chlorination mechanism, what I want you guys to do is to do the exact same thing that we did before, and then check with your neighbor and make sure that you've got everything set up correctly. The only difference with this is we're using aluminum as our metal instead of iron. So I'll give you guys a minute to draw out the full mechanism for this, and then check with your neighbor to make sure that you've got the same mechanism. Yep.
Is the net dipole being induced as it comes closer to the chlorine? Because it's not really the empty orbital itself that's attacking it, is it?
No, in this case, if you think about chlorine or bromine, there's no permanent dipole.
Right.
However, the lone pairs on there can act as a weak Lewis base, and so they'd be happy donating electron density to that empty p orbital on aluminum.
So essentially they're attacking the empty orbital.
Mhm. Once you think you got the mechanism, give me a thumbs up so I know. Show of thumbs. Yeah. All right, so let's get going with this. It's okay if you're not done yet. Just like before, the chlorine's going to donate electron density to that empty p orbital. We're going to form this super duper strong electrophile. I'm not going to show the geometry here just to save time. Okay, so now that we've got this, we've got a super strong dipole, just like I said before. And then in your next step, your aromatic ring is going to act as your nucleophile. It's going to attack this chlorine, kick off our leaving group. And then what's our last step?
Chlorine bond.
Yeah, exactly. The chlorine's going to deprotonate. It's going to restore aromaticity. And we're going to regenerate our catalyst. And our byproduct in this case is going to be HCl. Oh, sorry. I got iron on the brain. All right, so if we look at this, oftentimes organic chemistry students are like, great, another reaction for the memory bank, right? Why is this such an important reaction? Does anybody have an idea why?
Functionalize aromatic.
Yeah, you can functionalize them. What can we do with carbon-halogen bonds in order to make that carbon nucleophilic? Grignards, right? So we can throw magnesium into these systems, and now all of a sudden we've got a benzene ring that can act as a super duper strong nucleophile, and we can have it add into ketones or aldehydes and things like that. Hint, hint, wink, wink. Make sense? All right. So let's go on to one more. I think we have time for one more at least. Yep.
Is the intermediate the one with the positive and the non-aromatic ring bond, right? Is that isolatable?
Yeah, that's a good question.
Transition.
So Brian's question was, is this rhenium ion something that you can isolate? It's so high energy, you can't. However, you can observe it using spectroscopy And so we know that it exists. We know that it goes through this reaction pathway. However, it's not something you can get a bottle of and leave on a shelf. At least not that I know of. That is a good question, though, because anytime you're a chemist and you want to figure out how a mechanism proceeds, one way of proving your mechanism is the correct way and not another one is by showing that it goes through one intermediate and not another. That's a good question. So let's go on to sulfonation. I know you guys are like, 3 reactions already? What is this?
No, I'm used to it. Turn 2.
This was last in turn 2, right?
So we'll do one more cool reaction. Let me clean this up a little. These are oxygens and a sulfur and an OH. Does anybody know what that functional group is called?
Sulfonic acid.
Sulfonic acid, right? So if you look at it, it looks like sulfuric acid, right? So it's a sulfonic acid functional group. These are really common in organic chemistry. And this is a really useful functional group for electrophilic aromatic substitution. In order to get this functional group installed, you have to use something called fuming sulfuric acid. And I'm always amazed how many experienced chemists have no idea what fuming sulfuric acid is. Does anybody here know what fuming sulfuric is?
It's sulfur trioxide
Yeah, it's
gas with the sulfuric acid.
exactly. So what you do is you take sulfuric acid and you bubble through sulfur trioxide gas and you saturate your sulfuric acid with sulfur trioxide gas. The active reagent here actually isn't the sulfuric acid, it's the sulfur trioxide that's dissolved in it. This sulfuric acid in this case is more or less acting as a solvent. It's a really, really harsh solvent, but it's necessary in order to dissolve the sulfur trioxide. So let's take a look at what sulfur trioxide does. So fuming H2SO4 has SO3 added. And sulfur trioxide is kind of a weird molecule. You can draw it this way. However, it has a very, very major resonance structure. Where this oxygen has a negative charge and that sulfur has positive, and you can show even more resonance structures with this, right?
Yep.
Makes sense? Does anybody know the problem with sulfur trioxide?
Probably high reactivity.
A practical problem with our environment?
Sulfur.
Sulfur, yeah. Sulfur's never fun. It's stinky. Has anybody studied acid rain in their bio classes? So sulfur trioxide is produced whenever you burn coal. So when you burn coal, the sulfur trioxide goes up through the smokestack, and if it's not scrubbed, that sulfur trioxide will react with water in the air and form sulfuric acid, which mixes with the rain, goes down into the forest, and kills a huge portion of the ecological system around coal-powered plants. This is a really, really big problem, and it's something that can be mitigated by adding scrubbers onto the tops of these coal power plants. However, really it becomes a best-case scenario of minimizing the sulfur trioxide. There are areas in West Virginia where, I'm not even kidding, you can see a power plant by the air, and then if you follow the downwind side, you can see this swath of dead forest. So it's a really big issue, and it's something that I think people in the popular culture think we've got under control, this idea of clean coal. The reality is coal will never be clean. It's just something we can minimize the damage from.
What do they use as scrubbers? Just some kind of a proton donor to...
That's a good question. I'm not sure the exact chemistry that goes on. There's a lot of various things they're trying to remove. So oftentimes nitrogen gases too, so NOx's, sulfur gases, things like that. Anything that's an impurity in the coal, they're trying to trap so it doesn't get
So they have
released.
something that they can react and bind onto, right?
Mhm.
Oxygen can just latch on to like a proton or something.
Yeah, scrubbers basically chemically react with these so that they're either inert and non-harmful or they trap them all together.
Right.
Yep. All right, so if we look at this, sulfur trioxide is a very good electrophile. And this is important for that electrophilic aromatic substitution chemistry, right? So let's take a look at this as a very good electrophile. Okay, so we've got this sulfur trioxide. It's a phenomenal electrophile. We know that aromatic rings can be a relatively weak nucleophile. They've got that electron density. So all it's going to do is attack the sulfur center and kick up electrons over to that oxygen. Let me clean this up a little. So we go through this uranium ion intermediate, just like we did before. And then in this next step, it feels a little bit out of order. But bear with me. You can use the conjugate base from sulfuric acid as a weak base. It doesn't make sense, right? Why would this act as a base? What's driving this reaction forward?
The negative on the
Right? Normally I would say this is the world's worst base. It's not going to steal. Exactly. By restoring aromaticity, we're pushing the reaction in the forward direction. That's the main driving force in this reaction. You don't need a very strong base at all. So in this case, it's going to grab this proton, restore aromaticity, and now you've got your sulfonic acid installed. And you've created sulfuric acid in the process. One neat thing is we're going to be doing a variant of this reaction during lab. It is a reaction you have to be very, very careful with because you use very strong concentrated acid. And this quarter in particular, I'm not going to joke around with safety procedures. If you're not ready for lab, I won't let you in lab. So like I said, make sure you come dressed appropriately. Yep.
Can you talk about the final protonation step for the sulfonic?
Oh, sorry. I skipped ahead. Thank you. So at this point, there should be a negative charge on there. We've got sulfuric acid, and then this can act as a proton donor. Thank you, guys.
So it's taking a proton off of itself and then giving it back in a good spot.
Mm-hmm. Yeah, in this case, it is in equilibrium in this last step. However, the equilibrium can favor that sulfonic acid with the proton.
Is it sterics that's preventing it from doing it intramolecularly, like doing it to itself?
Yeah, exactly. At least I don't think there's any experimental evidence saying that this negative charge up here can do that deprotonation on itself. I think geometrically it's very unfavorable. However, you could argue that maybe two molecules collide and do that.
Do it.
Yeah, as some sort of dimer. However, most people show it using this mechanism. Okay, so after this step, we've got our conjugate base of sulfuric acid as our byproduct. This is a useful functional group for aromatic compounds. However, I think the neatest thing you can do with this is you can actually reverse this back off. In order to do the reverse reaction and go back to your starting material, all you need to do is treat this with dilute sulfuric acid and it will go in the exact opposite direction. The question is, well, why would you do that? Does anybody have an idea why?
protecting group.
Protecting group. You could protect a carbon on your aromatic ring, block it from doing any sort of chemistry, and then remove it when you're done. That's exactly what it's used for. So at this step, dilute H2SO4 will take you right back to your starting material, and you can remove that blocking group.
You could just add water.
Yeah, essentially you could add water. Normally you'll do this sequentially, so you'll add in your sulfonic acid functional group, do another reaction, and then remove it later on. Does that make sense?
Yeah.
So let's make a little note here. This is a good blocking group. let's see, I think we only have a few more minutes. So what I'll do, instead of continuing on to the next reaction, is I'll give you guys a couple minutes to look at the pod. Like I said with the pod, I want you guys to show the full mechanism. I'm going to be focusing a lot on synthesis this term, and we may pull from reactions from last term or even first term. So if you are rusty, make sure you go through previous material that we covered in the winter or spring or fall.
Have we covered enough today to do the following?
Yep.
Yeah.